The next topic is the magnitude of a vector. As you remember, we defined a vector as a mathematical object that has direction and magnitude. The magnitude or length of the function, or when you're taking linear algebra, you're going to talk about the norm of the vector, is the length of any of its representation, and it's denoted by, you either use two vertical lines to the left and right of V, or you're using two sets of vertical lines to the left or right side of your vector. We're using a distance formula to compute the length of the line segment, or in this case, your vector. So if your vector has only two components, A1 and A2, which is your X and Y, the magnitude or length is equal to square root of A1 squared plus A2 squared, or X squared plus Y squared. And in 3 dimension, you're going to add the Z component as well. So here you have your X, you have your Y, and you have your Z. Let's take a look at this example. Suppose you have two vectors like A and B. You want to find the magnitude of them. What's the norm? What is the length? Remember the magnitude formula. The magnitude is square root of the very first component to the second power, the second component to the second power, and the third component to the second power. For the first vector, the first component A1 is 4, A2 is 0, and A3 is 3, or these are your X, Y, and Z. Again, these are X, Y, and Z values of your vector. So my first vector has length square root of 4 squared plus 0 squared plus 3 squared, which is square root of 16 plus 0 plus 9, or you have square root of 25, which is 5. So the length or norm or magnitude of the first vector is 5. We can take a look at these vectors in 3D as well. So let me find the magnitude of the second vector and then visualize these. The magnitude of B is equal to B1 squared plus B2 squared plus B3 squared. And these are your X, Y, and Z again. These are the components of your vector, which is equal to square root of -2 to power 2 plus 1 squared plus 5 squared, or you get square root of 4 plus 1 plus 25, or basically you have square root of 30. So sometimes the length of the vector is very beautiful, like easy to compute, like 5, or you might see something like radical. Eventually, you can use a calculator to approximate these values. But the main topic here is we use the norm or length of a vector to normalize the vector. This is very useful, especially in the case that you are in machine learning algorithm or deep learning algorithm and you need to normalize your vector by dividing the vector component by its length. So let's take a look at our visualization. Find the position vectors. So the very first vector, vector A, has component 4, 0, and then 3. So this is your very first vector. And the second vector, I'm going to add another object for you, has components -2, and then 1, and then 5. So this is your second vector. As you can see, they have different lengths, they have different magnitude. The distance between the origin and to the terminal point is going to be different. Now the question is, what if we have two vectors? What if we have three vectors? What operations are available? We can basically take two vectors and add them together. We have different ways to find the sum or addition of two vectors. One of them is parallelogram law. The other one is basically triangle law. This one that we're going to represent is triangle law. You have two vectors like v and w. This is my vector v, and this is my vector w. And what I'm going to do, I'm going to use the translation of vector w that I'm going to call w prime. So w prime is equivalent to vector w. As you can see, they are parallel to each other. Here we go. This is my vector w, all right? And we're using the translation of vector w, and then I'm going to add these two vectors by writing their sum as v plus w. This is triangle method. You could also use parallelogram law, which gives you the exact same result, right? If you look at v plus w here or here, you basically have the exact same vector using two different methods, either translating one of the vectors and finding the diagonal, or using parallelogram method, which is basically saying that, hey, you have two vectors v and w, and you have the summation of these two vectors down here. Let's solve some examples to feel more comfortable about this method. Suppose here I have two vectors and I'm going to add them together, like -1 and 4 plus 6 and -2. The question is, does it really matter which one we write first? 6 and -2 plus -1 and 4, right? So take a look at this. Here, if I add these two together, I'm basically taking corresponding components and add them. Here I have -1 plus 6, comma, and then I'm going to take y components, add them together, comma, 4 minus 2, which is 5 and 2. But is the order important when you're adding two vectors together? This is going to be, well, again, I'm going to take the very first components and add them together, which is 6 minus 1, and then I'm going to take the second components, -2 and 4, and add them together, which is -2 plus 4. Here you have 5 and 2 again. These two are the same. So basically, it doesn't matter if you add u to v or v to u. You're going to get the exact same result. The same as here. Here I'm going to add these two vectors together, 3, 0, 1 plus 0, 8 and 0. So of course I'm going to start by adding the first components, 3 and 0, and then the second components, which is 0 and 8, and the last components, which are 1 and 0. Now we have z components as well, 1 plus 0, which is obviously 3, 8, and 1. So the order is not important, right? We expect to get the exact same result. The same here, 3 and -1 plus -1 and 5, which is going to be 3 minus 1 and -1 plus 5, or 2 and 4. Another operation is called scalar multiplication. For a scalar c, what is a scalar? Scalar is just a number. For a scalar like c and a vector like u, the scalar multiplication C times U, or CU is basically distributing C over the components of vector U. If C is positive, then C multiplied by U, or the scalar multiplication between C and U, is going to be in the same direction as vector U. This is this case here. I have my vector U down here, and C is positive. C times U gives you a larger vector in length, but it's in the same direction. So this is this case when C is positive. When C is negative, however, you're going to get a vector in the opposite direction. So here we go. Here I have my vector U, and I'm going to multiply that vector U by a negative number. I'm going to get a new vector in the opposite direction. This is my CU. Please note that the magnitude of this new vector is the absolute value of the scalar times the magnitude of vector U. So here we go. This is the length of CU, which is the absolute value of C. This is absolute value of C times the magnitude of U. And we have a nice observation here. U minus V is nothing but U plus negative V. And negative V is basically the scalar multiplication of -1 times V. This is the opposite of vector V. So if you have a vector like V, negative V is going to be in the opposite direction of vector V with the same length. So the vector difference of U and V is basically addition between U and the scalar multiplication of -1 and V. Example for you. Here I have vector A and B. I want to find A plus B, A minus B, 3B, and 2A plus 5B. Let's begin. So A plus B. A plus B is easy for you because you have 4 plus -2, 0 plus 1, and 3 plus 5. Here you have 2, 1, and 8. The second one is A minus B, or it is A plus -1 times B. My A is 4, 0, and 3 plus -1 times B, which is -2, 1, and 5. This is equal to 4, 0, and 3 plus 2. You're basically now distributing this negative sign into each component of your vector. So you have 2, you have -1, and then you have -5. Now just take the corresponding components and add them together. 4 plus 2, 0 minus 1, and 3 minus 5, which is 6, -1, and -2. What is 3 times B? Okay, for 3 times B, it's a scalar multiplication of 3 by components of B, -1, -2, 1, and 5. So basically, it's just a distribution. So what do we get? We get -6, 3, and 15. And finally, what is, let me change this to this color, 2A plus 5B. So 2 times A is vector 4, 0, and 3, plus 5 times vector B, which is, let me see what was B, -2, and 1, and 5. So this is equal to, now you just distribute this element into the components of your vector and then eventually add them all together. This is 8, 0, and 6 plus -10, 5, and 25. So this is equal to 8 minus 10, 0 plus 5, and 6 plus 25, which is -2, 5, and 31. Different operations, so addition, subtraction, scalar multiplication, and addition between scalar multiplications. You can visualize these as well. It's a good practice to take a look at your 3D website and visualize